In the previous videos, we've gone over finding the integrated rate law and the half-life for a zero-order reaction, first order and second order. And these are the ones which we calculated. Now, let's go over some questions. We see how we are able to answer some. Now, in the first question, we'll be given, consider the reaction known to be a zero-order reaction in A and has a rate constant of 5.0 times 10 power negative 2 molar per second at 25 degrees Celsius. Alright, now the question is, an experiment was run at this temperature when the initial concentration was this value we can see. Now write the integrated rate law for this reaction. Well, the integrated rate law, this is a zero order reaction, and the integrated rate law for a zero order reaction is the concentration at a certain time is equal to negative kT plus the initial concentration, as we already determined. Alright, now using this one, calculate the half-life for this reaction. Now, calculating the half-life, we have already determined the formula for half-life of a zero-order reaction, and half-life is actually given by the initial concentration divided by 2K. And so in this case, the initial concentration has been given there. So the initial concentration is 1.0 times 10 to the power negative 3 molar. And then 2 times K, the equilibrium constant or the rate constant, is been given at that point, which is 5.0 times 10 to the power negative 2. It is in molar per second. So let's go on and do the multiplication. So down there, it will become 2 times 5, that becomes 10, and then 10 to the power times 10 to the power negative 2. And then on top, what we have is 1 times 10 to the power negative 3. And then if we divide them, what we are going to get is 0.01. So we can see molar and molar is going to cancel. This is per second. If it goes on top, it becomes second. So it is 0.01 seconds. And then the other one, find the concentration after 1.0 times 10 to the power negative 3. Find the concentration after 1.0 times 10 to the power negative 3. This was actually supposed to be seconds as elapsed. This is the time that elapses and not concentration. And so using the same formula we can see here. So we are talking of the concentration where there is T after 1.0 times 10 to the power negative 3 seconds. That is going to be equal to negative where there is K, the equilibrium constant or the rate constant, that is 5.0 times 10 to the power negative 2. Okay, and then the time is the same, 1.0 times 10 to the power negative 3. So this is in molar per second, and then this one is in second. We can see now the second and the per second is going to cancel out, so we're going to remain with molar, and then plus the initial concentration, and the initial concentration is 1.0 times 10 to the power negative 3 molar. So what we are going to have here is, of course, there's a negative in front there, so we go on and say 5 to the times 10 to the power negative 2 multiplied by 1 times 10 to the power, that is a negative 3. That is going to give us negative 5.0 times 10 to the power negative 5 molar. And then plus 1.0 times 10 to the power negative 3 molar. So that gives us, so what we are having, negative 5.0 times 10 to the power negative 5 plus K plus 1.0 times 10 to the power negative 3. So what we are going to get is 9.5 times 10 to the power negative 4. This will be molar. That is it then for this question. Another question given: a certain first order reaction has got a half-life of 20 minutes. Calculate the rate constant for this reaction. Now we've been told it is a first order reaction and we want to calculate the rate constant. We've been given the half-life. We know that for a first order reaction, the half-life is given by natural log of 2 divided by k. Well, the half-life is 20 minutes, so we'll put 20 minutes there, and that should be equal to natural log of 2 divided by k. So if we cross multiply, we are going to see that k is equal to natural log of 2 divided by 20 minutes, and so k is going to be equal to the equilibrium constant. The minutes is down here. Natural log of 2 divided by 20 minutes, so that is going to be 0.0347 minute to the power -1. That is because the minute has gone on top. Well, we can also use the formula to determine the unit for k. K is equal to m to the power 1 minus n, and then time to the power -1. So because this is a first order, where there is n, we're going to put 1. So that will be m to the power 1 minus 1, which is power 0, and then in this case time is in minutes, so that will be minute to the power -1. So any number is to the power 0, the answer is still 1. So this is the unit, minute to the power -1, as we can see there. Now the second part, how much time is required for this reaction to be 75% completed? Now let's say the initial concentration we started with. If the initial concentration we started with is 1 molar. Now what is 75% of 1 molar? So 75% of 1 molar, that would be 1 times 75 out of 100. That is going to be 0.75. So this is 75% of 1. So this is actually, okay, how much time is required for the reaction to be 75% complete? This 75 we can see here is what we are going to, what is going to be used up. Okay. Now we want it to be 75% complete. So what will be left if this is how much is used up? Because if this is the initial, 75% of this is going to tell us how much has been used up, and that is 0.75 has been used up. So how much has remained? So 0.75 molar is used up. So from this, what has remained is actually 1 molar was the present one initially, minus 0.75 molar. So the one which remains is 0.25 molar. So that is 75% to be complete. So this is what remains. This is what has been used. So using the one which remained, we can calculate the time. Now because this is a first order reaction, we can go on and use the formula. First order reaction, we know that natural log of the concentration at a certain time t is equal to -kt plus natural log of the initial concentration. So we are talking of the natural log of the concentration that is left out, that is 0.25, and that is going to be equal to negative k. The equilibrium constant we've already determined as 0.0347, and then times the time is what we want to find, and then plus natural log. Then initial concentration, we are taking it as 1. So natural log of 0.25 is negative 1.386, and that is supposed to be equal to negative 0.347 t, plus natural log of 1 is a 0. So if we want to have time, we divide both sides by natural log of 0.347. Also here by natural log of 0, I mean just by negative 0.347, not natural log. And so time is going to give us this one, and this one cancels. Negative 1.384 divided by negative 0.347. Okay, there's another 0 here. I don't know why I'm writing only 1 0. So there's another 0 at this point. So there is another 0 there, and then 347t. So what we are dividing by is negative 0.0347, then this side by negative 0.0347. And so the time is going to be, if you divide these two values, it will give you 39.95, well, which approximated just to 40.0 seconds. Oh, this is in minutes, not seconds and minutes. So that is the time that is going to be to elapse if 75%, if this reaction is supposed to be 75% complete.